Today I'm going to talk about the concept of thermal relaxation time in photothermal laser treatments. In particular, I'm going to talk about the problem that this gives us in the theory of selective photothermolysis. I gave this presentation at the BMLA meeting last week in Edinburgh. So let's say it's morning and we want to boil some eggs. So we put a pan of water onto the cooker and we raise the temperature to boiling point, so that's 100 degrees Celsius, and then we put in the eggs. How long do we cook these eggs for? Well, is it 1 minute? Is it 2 minutes? Is it 3.5 minutes? How do we choose it? Do we choose this cooking time based on the egg's cooling time? Well, the answer clearly is no. You don't cook something based on how quickly or how slowly it cools. And yet that's what we do with laser treatments and IPL treatments because we constantly think about the thermal relaxation time. In actual fact, this is not the way to consider this. The idea of thermal relaxation time was introduced by Anderson and Parrish back in 1981 when they proposed the theory of selective photothermolysis. The idea behind this was to target something in the skin using an appropriate wavelength, which would maximize absorption in that target, an appropriate fluence to ensure that we generated the right sort of temperatures, and also the appropriate pulse width. Now, they chose a pulse width to match up to the relaxation time of the target, and this was chosen to minimize thermal damage to everything else around the target. But this actually is not the best way to approach this particular issue, as we'll soon find out. Anderson and Parrish showed us an equation. This equation here, the relaxation time is the square of the target radius divided by the thermal diffusivity and a geometric constant C. In cylinders such as blood vessels, C equals 4. And this is the time it takes for the maximum temperature in a Gaussian distribution to decrease by 50%. So in other words, it's the time it takes to cool by 50%. Now, while this is all well and good, it actually misses something rather vital, which I'll come on to soon. In 2001, Altshuler changed it or added a new definition of thermal damage time. They decided that we should consider the pulse width plus the time it takes for the heat to transfer to the follicle wall. The follicle wall is where the germ cells or the stem cells live, and these are the cells that we must destroy if we are to kill the follicle and prevent new growth. So of course this takes a lot more time than the original relaxation time, and in fact they found that it increased the relaxation time by a factor of between 6 and 23, depending on the size of the follicle you're considering. But neither of these definitions take into account the time it takes for the proteins in those cells to denature. So this is where the flaw lies. It's all fine and well heating up the hair and allowing the heat to transfer out to the follicle wall, but if we don't cook the germ cells sufficiently long, then some of the cells, or in fact even all of the cells perhaps, may survive the process and continue to grow that follicle. So how do the relaxation and damage times compare for hair? If we look at 3 hair diameters, 50, 100 and 150 micron diameters, then the Anderson and Parrish formula tells us that the relaxation time is between 1.1 and 10.1 milliseconds, so a fairly short time. But the Altshuler thermal damage time is considerably longer. As you can see here, it ranges from 14 to 124 milliseconds. So that there is a significant difference between relaxation and thermal damage time, and yet still they don't account for the actual denaturation time of the germ cells. So what are we trying to do here? Well, what we're really trying to do is we're trying to denature the target cells, which are on the follicle walls, the stem cells. So this is a cooking process, essentially, just like the eggs. what are those cooking times? Okay, well let's have a look at this. If we have here a cross-section of a hair follicle, the stem cells you can see are on the follicle wall, and they can be up to 3.5 times the radius of the hair shaft itself. So we fired in some laser or IPL light. It scatters about all over the place in the dermis, and a tiny fraction will be absorbed by the melanin in the hair. This then is converted into heat energy, which raises the local temperature. As the heat spreads out, you can see from this image that we can get heat out to the stem cells, but the question is, will it be sufficient? So there are 3 times we need to consider here. The first is the heating time of the hair shaft itself, and that's what Anderson and Parrish essentially considered. The second time is how long it takes the heat to conduct out to the follicle walls where the germ cells live, and that's what Altshuler and his gang considered. But neither of them actually looked at the cooking time or the denaturation time of the germ cells themselves. And this is important because there's no point getting the germ cells up to a certain temperature and then allowing it to drop quickly thereafter, because that will not necessarily result in the irreversible denaturation of those cells. All of this can only happen during the anagen phase, as we know, but I recently discovered that the anagen phase can have at least 6 subphases during that particular phase, and I suspect that this process probably only works in the last 3 or 4 of those subphases. So what are the distances involved here? Because that'll give us an idea of the timings. Well, again, if we look at these 3 hairs, 50 to 150 microns, then the follicle walls diameter range between 175 and 525 microns, which is quite a significant distance from the melanin in the hair shaft themselves. So we need to ensure that the heat energy can diffuse out to these distances and maintain a suitable temperature for a suitable length of time to ensure that those germ cells are properly cooked. So I came up with a one-dimensional thermal transfer model like this. We can see here in the middle there's a 100 micron diameter hair shaft. The germ cells are on the walls, which are on 350 micron diameter, and then outside of that is the dermis, and the green and yellow temperature there is background temperature. So we heat up the hair shaft using light, and because the melanin is concentrated in the hair shaft, that's the bit that gets hot. So that's where the heat is generated. That heat then diffuses outwards, all around, all directions, and some of it will warm up the germ cells on the follicle walls here, as you can see. So the question now is, how do we make sure that there's sufficient temperature and duration for this to kill the germ cells? So this is a graph of the amount of denaturation known as omega. You can see the end of the pulse is at 10 milliseconds in this particular instance. I've chosen quite a thick hair here, 150 micron hair, irradiated with 12 joules per square centimetre. So not an awful lot of denaturation occurs until this point, 60 milliseconds after the end of the pulse. That's because it takes that amount of time for the heat to diffuse out to the germ cells and then start to raise the temperature of those cells to begin the denaturation process. That process then increases until it peaks at about 210 milliseconds. So there's quite a long time of denaturation. That's about 130, 140 milliseconds worth of denaturation before it peaks. And then there's a lot of denaturation after the peak, as you can see in the tail of this. In fact, this goes up to over 650 milliseconds, which is 0.65 seconds in the real world. So this is the amount of denaturation rate, I should say here. The actual accumulated denaturation is this orange line. This is when you actually add up all those little bits of denaturation. And you can see from this graph, that no significant denaturation begins until around about 100 milliseconds. So that's 90 milliseconds after the end of the pulse. We start to see some sort of accumulated denaturation there. Once this line reaches a value of 1, you can see on the right hand axis there, then these cells are deemed to be irreversibly denatured. In other words, they're dead and they cannot regenerate. But as you can see from this curve, this takes up to 650 milliseconds in total to reach that point. Given that the relaxation time of this hair is 10.1 milliseconds, it's difficult to see how the relaxation time can relate to the denaturation time. There appears to be no direct correlation whatsoever. So I suppose the question is, how does the amount of denaturation vary with pulse width? If you change the pulse width of your device, how will that affect the total amount of denaturation? So I chose for this particular case, the first part of the study, a 50 micron diameter hair. I chose a pulse width of 10 milliseconds, which is kind of fairly commonly used out there. And this basically determined that a fluence of 10.2 joules per square centimetre was required to ensure that we achieved irreversible denaturation. In other words, an omega of 1. So that's my arbitrary starting point. I have to start somewhere. And you can see that as the pulse width increases above 10, that the amount of denaturation decreases. So longer pulses in this instance are not beneficial, whereas shorter pulses down to about 3 milliseconds will actually give us a little bit more denaturation than we find at the 10 millisecond pulse. Interestingly though, once you drop below 3 milliseconds, the total denaturation at the end of this process again drops below 1. So it's quite clear here that for this sized hair and for this fluence, that the optimum pulse width is going to be between 3 and 10 milliseconds in this particular instance. So what happens if we look at this for larger hairs? So the green line represents a 150 micron diameter hair. In this instance, I had to apply a 12 joule per square centimetre fluence to achieve an omega of 1 at 10 milliseconds again, keeping the pulse widths common here. So again, in this instance, you can see that the total amount of denaturation decreases both at short or shorter pulse widths and at longer pulse widths, although not the same as we found for the 50 micron case. And then just to add into the mix, I've stuck in a 100 micron diameter hair in red, and you can see it's very similar to the 150 micron. So they're both much flatter than the very small diameter. So that tells us that the larger hair diameters are actually a bit less sensitive to the pulse widths compared to the small finer hairs, and it does suggest that for fine hairs we should probably be using shorter pulses at the required fluences. So what are the right times to consider for these treatments? Well, what we're trying to do to achieve a good result is to irreversibly denature the germ cells or the stem cells of the hair follicles. By doing that, you can effectively kill the follicle permanently, and that follicle can no longer generate new hair. To do that, it appears that we need to use pulse widths in the range typically around 3 to 30 milliseconds or thereabouts. I am still doing some more work on this to try and pin this down even more finely. But this all depends on the fluence. If you have insufficient fluence, then the pulse width doesn't really matter. You're never going to get a result. Imagine trying to boil an egg at 50 degrees centigrade in your pan of water. You'd be there all day, all month even. So what we found is that the denaturation time of the cells, the germ cells, is not dependent on the target's cooling time. In other words, it doesn't depend on the relaxation time. That's not really the critical time at all. The cooking time of the gem cells is not equal to the cooling time, which is what TRTs and TDTs are. So the Anderson and Parrish relaxation time equation doesn't really apply in the real world, because the flaw is that that particular time and the alveolar damage time do not consider the time that we need to fully denature the target cells, which ultimately is the whole point of the treatment. It's the denaturation times of the germ cells that's important, and the denaturation time depends very much on the local temperature, which depends on the fluence. So, in conclusion, the success rate of all of these photothermal processes depends on the temperature rise in the target and the denaturation history of the target cells. In other words, are we cooking them for a long enough time at the correct temperature? Which means that the success depends on the fluence, because that's what determines the temperature rise, and the temperature time history of the targets, the follicle size or blood vessel size if you're looking at blood. But definitely does not depend though on the cooling time or the relaxation time of these targets. There's no direct correlation there at all. And this research shows that in actual fact, fluence is the critical factor here, not so much the pulse widths. With pulse widths you get a lot of leeway as long as you have the correct fluence. But if your fluence is not sufficient, then it doesn't matter what pulse width you use, you're never going to get a good result. Thank you for listening. I hope this made some sense. You can find some more material on this kind of issue and others at my blog here. Thank you.